Okay, hello everyone. I hope you can hear me and I hope you can see my screen. I have to apologize again for recording this lecture and posting it online. Uh, I'm out sick for a few days. Hopefully, I can be back in class next Tuesday, so our next class can hopefully be in person. So, last time we started talking about rigid body kinematics. Specifically, we started talking about rotation, about a fixed axis. Excuse me. And we reviewed the right hand rule and how you can use that to find velocity acceleration directions in the vector form for any point on a rigid body. We also found that any line on a rigid body will have the same angular velocity omega. So let's do a sample problem. This is sample problem 5.3. I think some of you in one of the sections I did this example. So if you've seen the solution of this example, then feel free to skip ahead for a few minutes and go to relative velocity. Okay? All right, so let's read the problem. So there's a right angled bar that rotates clockwise. So it's rotating like that about this point. And the omega, the angular velocity, is decreasing at a rate of 4 radians per second squared. It wants us to write the vector expression for the velocity and acceleration of this point when omega has a value of 2 radians per second. Okay, so first thing is that what is the direction of z? So if you use the right hand rule, and I hope you know how to do this. If you don't, we can review it again in class because it's easier to show in person. Z or K will be pointing out, right? How about omega? So if you remember right hand rule for curve orientation, if you're if you curl your finger and they're in the direction of this omega, then that means that the vector orientation of omega will be along your thumb, right? So what would that be here? That means that omega is pointing in, right? But z, we found that is pointing out. So when I write the vector form of omega, that means that omega at when the omega is 2 radians per second the direction is negative k. Okay. We also know that alpha is in the same direction, right? We know that alpha is decreasing, so it does have a negative itself. So basically, it's going to be minus 4 radians per second square, or 4 radians per second square. Sorry, it's along k. Okay, so we found the vector form of omega and alpha using the right-hand rule. Now, we want to find v, at, and an, right? So that's easy. We have the equations for that. V is omega cross r. So what is r for a? The r from the fixed axis rotation to our point of interest, which is a. So let's write that. R is equal. So note that the x-axis and y-axis are given. X is along this r. So if I want to write it in ij notation, r is 0.4 I plus 0.3 j. Okay. Now let's compute omega cross r. Omega is minus 2k, r is 0.4 I plus 0.3 j. Now we have to remember how to do this. I, j, k. Okay, so we know that if you go along this clockwise orientation, then for example, I cross j, that would be positive k. If I do j cross I, that would be negative k. Okay, so if we use that, what is the first term? That's minus 2 times 0.4, so it's minus 0.8, and k cross I, that's positive j. How about minus 2k cross 0.3j? So that's minus 0.6 minus 2 times 0.3, and k cross j, that is negative I, so this is going to be positive. Okay, so this is V of A. We also know that there is an AN and an AT. AN is omega cross R. Omega cross R is just V, which we just found. So I'm gonna write that. This is minus 2k crossed with V, which is 0.6 I. I'm just writing I before J because that's how we usually write it. Okay. So minus 2k cross 0.6 I, that's minus 1.2 J. Minus 2k cross minus 0.8 J, that's going to be negative 1.6 I. Okay. It's the second thing that we were after. Or let me write AT first. AT is alpha crossed with R. So alpha is positive 4k, right? Crossed with 0.4 I plus 0.3 J. So the answer of this is minus 1.2 I plus 1.6 J. Okay. And now if you want to write total acceleration, excuse me, that's AT plus AN in the vector form. So that would be minus 2.8 I plus 0.4 J. Okay. If you have any questions, you can email them to me, or I might have office hours today. So, or yeah, you can email me and I'll try to go over them next time when I'm in class, because I think it's easier to show some of this, especially the right-hand rule in class. By the way, today's class, this recorded lecture will probably be less than the usual time of the class. It won't be 1 hour and 40 minutes because I don't want to teach too much materials online like this, because I prefer the in-person method. Okay, so this is our example of fixed axis rotation. Now let's move on to the next section, which is on relative velocity. Okay, So the idea of using relative velocity for rigid body is that you determine the velocity of a point on a rigid body in plane motion, not plane motion, by adding the relative velocity due to rotation about a convenience reference point to the velocity of the reference point. So what does that mean? So here on the left, you have a body and there's a line AB on it, or BA, right? And this is moving and rotating in space, okay? Now, the idea is that if I look at point A relative to B, if the observer is sitting on B, then it sees that point A is going through a circular motion. So it's kind of like a fixed axis at B. And vice versa, if the observer is sitting at A and I look at the motion of B relative to A, then it looks like that B is going on a circular path where the center is at point A, okay? And from here, we can see that this delta R A, the change in position of A from A to A prime, is equal to delta R B, which is this vector, I just moved it here, plus the relative motion, delta R A relative to B. Now, if I divide both sides of this by delta T and take the limit, that means that delta R over delta T as VA is equal to VB plus VA relative to B. Okay. And the idea is that the VB is that convenience reference point, hopefully, so you can write VA as VB plus the relative velocity. Now, if I look at VA relative to B, as I said, that looks like a circular motion, so I can write it as R omega or omega cross R, right? That was a fixed axis rotation. That's the equation we found before. Okay. Here we talk a little bit about interpretation of this graphically. So this is the path, that absolute path of point B. This is the absolute path of point A, and these are the velocities, absolute velocities. Okay. Now, what I'm doing is that I'm writing the VA as VB because it is moving with VB, right? Plus VA relative to B. And VA relative to B, as I said, this is fixed axis rotation. So if I'm sitting at B, I don't see my own movement. So it's like a fixed axis rotation. I don't see that B is rotating, right? To me, A is rotating in the circular path. And so VA, the vector velocity A, is equal to velocity B plus relative velocity. Okay. Again, if you have any questions, please write them down and send them to me. So here are some notes about this solution. Theta dot omega is the absolute angular velocity. The linear relative velocity is always perpendicular to the line joining the 2 points. That means that this VAB, that's always normal to R, which makes sense, right? Because it's a fixed axis rotation, so it's a circular motion. The solution of the relative velocity equation may be carried out by scalar vector algebra or a graphical method, and the choice depends on the problem really. Okay. Now let's do an example to kind of show what we mean. So this is a sample problem 5-7 for the 9th edition. So there is a wheel of radius r 300 millimeters. Okay, that's this. This is r, it's 0.3 meters rolls to the right without slipping. That's important. And has a velocity VO. That's the V of the center, right? The VO is 3 meters per second and it's going to the right. It wants us to find the velocity of point A on the wheel for the instant shown, okay? So A has a radius of 200 millimeters, and when this angle between horizontal and line OA is 30 degrees. Okay, so what we want to do is we want to use relative velocity, right? And as I said, there are different ways to do this. The method that we're going to use is scalar geometric. In your textbook, it solves the same question using the vector method. The next question that we do, the next example, I'm going to solve using vector. Okay, so the idea is that I want to write the velocity of A relative to a convenient point. And by convenient point here, I mean O is my reference because I know its velocity, right? So it makes sense. So I'm going to write VA as VO plus VA relative to O. Okay. Now this angular velocity, the angular velocity of AO, this line, we know that's the same as the angular velocity of the whole wheel, right? We talked about that in rigid body, omega of any line is the same, right? For any two lines, omega is the same. And so what is VA relative to O? That's going to be this radius, RO, theta dot or omega. Okay, so what is this omega or theta dot? Let me write it as omega. So omega, I know that this is not slipping this point, right? So that means that for a moment, for this moment, this point has no velocity, right? Because its velocity, the velocity of this point on the wheel should be the same as the velocity of this point on the substrate, on the surface, right? Because the substrate is not moving, so this point shouldn't be moving. Okay, so I can write, so before I do this, I want to find omega. I can write VO is equal to omega R, or R omega. These are the scalar form, right? We're doing the scalar method. So that means that omega is VO over R. It's 3 meters per second, and this is 0.3 meters, 300 millimeters. So omega is 10 radians per second. Okay. Now going back to point A relative to O, that's going to be this radius, 0.2 times my omega, which is 10. So V of AO is going to be 2 meters per second. Okay. Now, I know that let me copy this and take it here. Okay. So I know that VAO is normal or perpendicular to OA. Okay. I also know that VO is in this direction. So VO is to the right. And I know VAO is normal to this line. So VA is going to be a vector like this, which is the sum of these two, right? Remember that vector VA is equal to VAO plus VO. Okay. Now, I also know the angle between these two vectors that when added together make VA. So there's something called the law of cosine, which I think I should go over in class, but you can also Google it. It gives you the length of the vector VA when it's the summation of these two vectors, and you know the angle between them. Okay, so VA is going to be the length of VA of VO, which is 3 meters per second. So 3 squared. 2 is the length of VA relative to O, and 2 times 3 times 2 and cosine the angle between them. Okay, so this gives me the length of VA, which is equal to 4.36 meters per second. Okay, so we are done. We know now the velocity of point A. Okay, so the idea was that it was not easy to write velocity of point A in the absolute sense, so I wrote it relative to O because I know the velocity of O, and then I used that to find absolute velocity of A. Okay, let's do another sample problem, but this one I'm going to use the vector method. Okay, so the question is that the crank CB, this crank, oscillates about C through a limited arc, causing crank OH to oscillate about O. When the linkage passes the position shown with CB horizontal and OA vertical, the angular velocity of CB is 2 radians per second counterclockwise. Okay, omega CB is 2 in the counterclockwise direction. For this instant shown, determine the angular velocities of OA and AB. Okay, so how are we going to do this? We can write VA as RA or omega OA cross RA, right? I know VA is omega OA, and this is the vector form RA. Okay, that's velocity of A because OA is rotating about a fixed axis, so I know how to write that. Omega CB, or sorry, V of point B, that's going to be omega CB cross this, which we're calling RB, right? This velocity. Also, I know that V A relative to B. So if my observer is sitting on B and looking at A, the velocity of A is relative to that. B is omega AB cross RA relative to B. Okay? B. All right. Now, I know VA, VB, and VAB. So what is the relationship between these three? I know VA is VB plus VA relative to B. So let's write that. Omega OA cross RA equal to omega CB cross RB plus omega AB cross RA relative to B. Okay, I just wrote VA is equal to VB plus VA relative to B. Okay, Now all we need to do is write the vector form of these vectors. So I don't know omega OA. I don't know its magnitude, but I know its direction. It's along K, right? How about omega CB? This rotation. I know that angular velocity is also along K, and I know its magnitude. And I also don't know omega AB, but I know it's along K. Okay, in this instance shown, what is RA? RA is vertical and its magnitude is 100 millimeters. So it's going to be 0.1 J. RB is 75 millimeters. And it's along negative I, right? Because IX is to the right and this is to the left. How about RA relative to B? So that you just need to do some calculations. So you need to find this distance and this distance, and those are along I and J, right? So you need to either find the angle, like you can find this angle here, and you can use that um, to find this length and this length. Oh, sorry about that. You don't really need to do this because you're given. So I know this length is 250 minus 75, so it's 175 millimeters. And I know this length, that's 100 minus 50, so that's 50 millimeters. Okay. So it's going to be negative 1.5 in the I and plus 0.005 in J because these are in millimeters. Okay. Now, all I'm going to do is I'm going to put these vector forms of omegas and r's into this equation. Okay. So let's call this equation 1. So plug in 1. That will give you omega OA K cross 100J. That's equal to, or not 100, sorry, 0.1. I mean, you can keep it as 100 as long as you keep everything in millimeters, right? So this is going to be 2K cross minus 0.075 I plus omega AB K cross RAB is negative 5 I plus 0.05 J. Okay, this is just equation 1 rewritten with the values of omegas and r's that we know. Okay, so if I carry out these cross products, that means that 100, or again, sorry, negative 0.1 omega OA, and this is not a vector, right? The vector part is the K. That's just the value of omega OA. So K cross J. Let's look at this again. K cross J, that's negative I. That's where the negative comes from. Okay. So minus 0.1 omega OAI. That's going to be equal to minus 1.5 J, 1.75 omega AB, J minus 50 omega AB I. Okay. Now I have two unknowns here. One is omega AB and the other one is omega OA. Do you know how I can find that? So the idea is that because this is a vector expression, you can match the coefficients of I and J terms, right? And that will give you two equations. So you will get something like minus 0.1 omega OA plus 0.5. Sorry about this. This is 0.05. So 0.05 I. Sorry, this is all in the I. This is equal to 0. So let me explain what I'm doing. We match IJ coefficients. Okay, so I coefficient, that gives you this, right? Because on the left-hand side, you have negative 0.1 omega OA, that's here. On the right-hand side, you have negative 0.05 omega AB with the I. If I take that to the left-hand side, it's going to be okay. And how about the J direction? In the J direction, I have negative 0.15 minus 0.175 omega AB. That's it, right? These two terms. The sum of these two should be 0. So two equations, two unknowns. If I solve it, I get omega AB equal to negative 6/7 radians per second, and omega OA is negative 3/7 radians per second. Okay, I mean, this last part is not really the dynamics, this is just the math, but the idea of the dynamics was that, let's remind ourselves what we did. The idea was that I wrote the velocity of A from the perspective of this fixed point O and from the perspective of this B, okay? And I know that VA is VB plus VA relative to B, so that helps me find the two omegas. Okay. Now let's move on to the last topic that I want to talk about today. It's about instantaneous center of zero velocity. So here the idea is that um, before we found the velocity of a point on the rigid body by adding relative velocity, right? Um, Relative velocity with where the reference point was some convenient point, which the velocity we either knew or was easy to find, right? Here, the idea is that that reference point can be a point which has and momentarily has zero velocity. Okay, so is there any point on the body which has zero velocity? And sorry, the example was this one, this example that we did, right? So we talked about, right, that point C here, for a moment, because this is not slipping, it has the same velocity as the ground and the floor, so it has zero velocity momentarily. So this instantaneous center of zero velocity, that's a unique reference point, which momentarily has zero velocity. Um, Let me point you to sample problem 5.7. And the answer is yes. Point C, because the wheel, it is not slipping. Okay. Now the instantaneous axis of zero velocity is an axis which is perpendicular to the plane of motion and passes through the instantaneous center of zero velocity. So what I mean is that if C is my reference point, or sorry, it's the instantaneous zero velocity point, then there's an axis which is perpendicular to this, to the screen, or the plane of motion, which is on the screen, and goes through this point. Okay. Now here it talks about your textbook, it talks about how you can find it. And it shows you basically three different cases. So the instantaneous center C is located on the perpendicular line to the velocity vectors, right? So that is always true. If this is velocity A, this is velocity B, then this instantaneous center C is on the perpendicular line to these velocities, right? These two lines. So you can match those. So you can draw these two lines and see where they match. Okay, and the C could be anywhere, right? It's not necessarily on the body. So here, it's not on the body. It's somewhere outside the body. Here, it is on the body. Okay, and because uh, omega is the same for any line on the body, I can use, for example, if I find point C, then I can use that. If I know the velocity of A, let's say if I know VA, I can use this RA, the distance from C to A, to find omega. Omega is going to be VA over RA, right? And that's the angular velocity of any line on the body. So I can also write VB as RB times omega. Okay? So that's how the center of zero velocity, instantaneous center of zero velocity, will help you find the V of any point. And here it talks about what is space-centroid and body-centroid? It's just the locus of instantaneous center. C in the space and in the body, you don't really need to worry about this. It's just a definition. Something that's important to know is that this instantaneous center of zero velocity has zero velocity, but it doesn't have zero acceleration. Okay, that's very important to remember. Now, the last thing that we are going to talk about today is we're going to do an example. The example that we did actually, example problem 5-7, we showed how you can solve that using relative velocity. Now we're going to use instantaneous center of zero velocity. Okay? All right, let's do that. And this is sample problem 5-11. Okay, so again, please read the problem. So we know it rolls to the right without slipping, and we know the velocity of the center O. Because this is not slipping, this means that C has zero velocity. Okay, that's the instantaneous center of zero velocity. Okay, now let's look at this diagram here in the bottom. I know velocity of O, and I know the distance from C to O from the instantaneous zero velocity point to the center, right? Do you agree that V of O is going to be equal to this R, right? From C to O, let's call that OC. That means the length of O to C times omega of the body. Okay? Now, omega of the body then is equal to VO over this length. VO is 3. That length is 0.3 or 300 millimeters. So I find omega to be 10 radians per second. Okay? Now, if we want to find the velocity of point A, now how can I do that? Now the question is, I know omega, right? I know how this is rotating with which angular velocity. If I know this length, then I'm done because omega, or sorry, VA is just length of AC times omega. Okay, so all you need to do is find the length AC. I mean, here it doesn't really give you this length directly. You know this OC length, you know OA, and you know um, the angle between them, so you can use law of cosines again. Again, I'll please remind me if I don't remember to go over this in class because it's important. So that means that this length of AC that would be equal to 0.3 squared plus 0.2 squared excuse me. Okay. And you don't really need to use this cosine laws, but I think it helps you. But so I'll go over it in class. But this gives us the length of AC is equal to 0.436 meters. Okay, so we're basically done. The length of AC is 0.436 times omega, which is 10. This length, AC times omega, and that is 4.36 meters per second. So that's what we were after, and it's this velocity. Why is the velocity drawn like that? Why is the vector like that? That's because we know that velocity is perpendicular to the line that goes from the instantaneous center of zero velocity to our point A. Okay. VA is perpendicular to AC. All right. So that's all we have for today's class. Again, I have to apologize for this. Probably my voice maybe wasn't great for teaching right now. That's because I'm sick, but hopefully, my plan is that on Tuesday we'll do some more difficult examples in class. Instead of sample problems, I'll do some exercises, and I want to keep those for the class because I want to first review everything that I did today. And also, I think some things are easier to show when you're actually in class and you're using the whiteboard, and I can like use my hands and everything. So I'll I'll solve some more examples from instantaneous center of zero velocity, one more difficult example, and one more difficult example from relative velocity. Please, I think I will upload these notes, and but this is a one-time thing, right? So hopefully on Tuesday I'll be in class, and then we won't have this kind of notes anymore. As I mentioned on Camino, your homework, the deadline has been extended until Friday. And if you have any questions, please email me. I will have online office hours tomorrow. I will also post that on, I'll announce that on Camino. So that's it. Thank you very much.